Video 26 on the foundations of the computational economics course is also a practical video where we'll be coding up a very useful class, which I called Polyline Class. It serves for the handy piecewise linear curve approximation. That's going to be useful for many tasks, including the midterm assignments. So, like I said, we're writing this useful class to represent a linearly interpolated function and also correspondences. So it could be a function that that sort of curves curves like this, for example. That's also going to be included. It is going to be useful for various models. And because I'm going to ask you to use it in midterm projects, we really need to cover it now. But the main idea under this class is precomputation. So a lot of the times we are working with models which include functions that take time to compute. And then it might be a good idea to pre-compute and approximate the function on a finite set of points instead of recomputing it every time you need it. That's the introduction. So let's look at the example where I'm thinking that this could give you an idea why Polyline class is useful. So think of market equilibrium. Now, it's just going to be a simple Marshallian cross, right? Supply and demand. But imagine that supply is subject to a batched production technology. And what I mean by that is that it's easy to produce a set number of items of this product, but then to increase it above a certain limit, a certain batch size requires an additional fixed cost. And so that means that the demand will slow down as the price increases. And there will be a sort of this ratchet effect or a wavy pattern. And so to calculate these effects, it might take some computational cost. Now, the demand, I assume, is affected by three distinct groups of consumers with different valuations for this product, and aggregating over these groups, which sort of join the customers for this product, also may take some time. So I'm thinking about the situation where the supply and demand curves are not easily computable. So then what we can do is we can actually use this class that we're writing now to approximate the functions for the demand and supply. And then it's not going to be hard to calculate the intersection of the piecewise linear approximation. And in fact, in one of previous exercises, we already looked at the intersection of two line segments. Okay. So here's some code. Some code that will that we take as a definition for the supply and demand. And I'm importing NumPy and matplotlib as always, ignoring the square root of negative numbers errors, similar to what we did with log of 0. And here's the code for supply. It's basically, it can take a value or a vector of prices and return the supply levels, and the same thing for demand. And we will treat these two functions as a black box. Well, what we can do, we can plot them just to get an idea of how they look like. And here it is. Here it is. How? You can see that following what I said, as price increases, the supply increases until it reaches some point where it's, where it hits some sort of a boundary here. And then to get a larger quantity, then the price has to grow even further to justify, a fixed cost of producing the next batch. And the same thing sort of happens again and again. So this is what I meant when I said the batched type of production. And here demand, if it was homogeneous, it would be just a line, but now it has these steps. This is 1, this is 2, and this is 3 steps that correspond to these 3 groups of consumers. Of course, this is all hypothetical, but imagine that these supply and demand lines are kind of not trivial, not the ones that you might be used to look at in theoretical or simple models. So what would be a straightforward approach to finding the market equilibrium? Well, we could just equalize supply and demand and solve this equation here using one of the solvers from the battery that we've already studied. But think about it. If we do a bisection method, for example, then we will have to calculate the value of the function many times every time we need to check the sign at the new point. So this function here will have to be calculated at least the number of times that we have iterations. And of course, bisection is not super fast. Now, for the Newton method to be applicable, we need to write a derivative of this function, right? And looking back at the picture, it might be hard, it might even be impossible. Well, of course, it's possible, but there are kinks here. Very, very clearly, there are kinks in the supply function where the function is not going to be differentiable. And this seems to be smooth and nice. So writing the derivative for the demand would be easy. But again, if we just treat the supply and demand as black boxes, then it's not easy to come up with the gradient, and therefore it's kind of hard to use the methods that we study, or it might be costly. Okay, what can we do instead? Well, here's the approach. It falls under the general idea of precomputation, and that's a technique to save time, essentially to reduce the runtime of different algorithms. The idea is that if you have to do something a lot of the times, but you have a possibility to do it only once, then you could precompute and then sort of use the precomputed values and plug and play, this sort of thing. So we can approximate supply and demand curves with our piecewise linear approximation. And when I say piecewise linear, it means that the function that we will use as an approximation function will have linear segments. How many segments, I'm not saying right now. So it could be a very nice piecewise linear approximation if we have a lot of grid points. But what's important is that it requires a fixed and known number of calculations of supply and demand. That's where the points are. And we can control the number of points. We can solve the model approximately, and then we can increase the number of points, or increase the number of points in the region of interest around the intersection, or around the approximated intersection. So this approach essentially gives us a lot more control. That's the point. And then we can consciously trade computational load and accuracy, right? And according to our application, we can start with low accuracy and compute something fast, and then maybe spend some time if we need accuracy. But computing the intersection of the piecewise linear approximations is fairly simple. Okay, to do all of that, we can create a tool, and this is what this exercise is about. We're going to write a class which implements all of these ideas and allows them to be used in many different models, that we may come up with. So this is going to be a class called Polyline. The idea is that it holds the coordinates of the computed points of the line. So it basically holds the grid of axes and the corresponding f of axes. That's what this is. And then it implements simple operations. We'll see which operations we need. And then it would be nice if it had a method to compute intersection points, and probably also graphing, since we know that visualizations are important. So here's a specification for the class that I have in mind. It should have an init function, of course, as to initialize itself. And the arguments for the initializer should be vector of x, vector of y's, and y's are f of x's. Just to be clear. And where f is the function that we want to approximate. And maybe a label. We want to use any type of data that are convertible to x and y's in the constructor, and this is just to make it more compatible with the rest of the code of the software of the code base. Now we want to write a string representation, so the wrapper will be the representation of this class. So it will be strings. We want a call. And this is an idea that this representation should be easily computable. So a call function would make the objects from this class act as functions. And here I wanted to be able to interpolate at any given points to interpolate the functions or return the approximation, calculate the approximation at any given points. Let's see how that is done. But we will need the tool, the interpolator. We will look at interpolation later in the course in greater details, but now we'll just use this tool from SciPy. And let's implement and add functionality so that we can put together, we can have addition for the objects of this class. And that can be done as for strings of text to concatenate polylines. Then we want a plot, and then we want an intersect, which would calculate the intersection points for the two polylines using the method that we've seen already and which is listed here below. And we can also have self-intersect. Self-intersect would be the routine to find intersections of this curve, in case it's a curve. Remember, it can be something like this. And then we want to be able to find this intersection point with the method self-intersect. Okay, so the task is really to write the code of the Polyline class. And I want to emphasize here that alongside the code development, we will start writing tests. And these are going to be unit tests, the tests that check the functionality of every small step, every small function that the class does. And then we'll run some graphical tests that I designed, or we can add some more. And finally, we'll come back to the equilibrium model that we started with and solve it, find the equilibrium using the Polyline class. So what follows is, as before, I'm going to be coding the class, and I think you might find it very useful to play back the video at the higher speed than normal. So I'm a little bit concerned that this video might be quite long. All right. Here's the theory for finding the intersection of the line segments, and we've seen this in exercise 9 before, so this is just a copy from there. To find an intersection point, we need to solve a little nice system of four linear system of 4 equations. Okay. So I'm ready to start coding, and I guess I'll go back to the normal Jupyter Notebook view here. So as you can see, there is no solution here except for the graphical test. So I'm just going to write this class now. All right, what should we start with? We have this list of functions that the class should implement, and let's start with these. So the initialization is going to be done with def double underscore init double underscore. and we want self is in all of the methods of the class, and it should take x's and y's as arguments, and this should be compulsory arguments, but then label as well, and by default say no label. Let's give it a docstring. Initializer of the polyline object. Now, it says here in the specification that all types that are convertible, should be without off, that are convertible to numpy array should be accepted in x and y argument. So the easy way to do it is to say x, y equals np, and p is imported already as array of x, and the same thing for y. So whatever is passed in the arguments will be converted to numpy arrays. But the thing is that we can run some tests in the cell below here. So let's run that in import numpy. So if I say a string and then print numpy as array of a, this is going to be totally fine. Okay, we don't want strings to be passed as x and y's, so we want to give it an explicit d type. What's d type? Should be float. Right, then if d type is a float, then then the string cannot be converted to floats, to numpy array of floats, and therefore there is a type error which is raised here. Okay, so I just want to say d type equals float to both of these. All right, and now we're already thinking about the test cases, right? So this initializer should produce a type error if something that is passed which is of the wrong type. And this is already some behavior that I'm describing here that can be tested. Let's this sort of thing is done by the unit test, and here's a little code snippet here about unit tests. We've seen this. We've seen this once before in exercise 6 if you've tried that, and let's do it here again, and I'll explain a little bit more. There's a link that is worth checking. You can see that the unit test is a testing framework, and it has a certain settings that we should follow. Here's a basic example. We import unit test. We make a class which should inherit the unit test case. And then we write down different methods in there and test different things, right, with these different assert statements. Okay, and then this is important as well. This is a usual trick which allows the class to be called as a function from the command line. But since we're in Jupyter Notebook, we're using a different trick here, which I already put in place. Okay, so test polyline, let's call it. And it's inheriting from unit test case. Let's say that these are for the Polyline class. And first test will be for the initializer. All right, so what situation have we thought about already? We want to be able to initialize the, we want to test that we can initialize the polyline with various formats of the data of x and y's that we may pass. And we also want to make sure that if we pass something that is not convertible to numeric numpy array, then an error is risen. Okay, let's look at how this can be done. there is a list of assertions that this testing framework can check. And here we are. So it checks for the equality, for not equality, for truth or false, checks for the is operator, which is essentially a strict comparison. Is not, is none, is not none in membership, not in, is instant, not is instant. Okay. Message keyword argument can be passed to assert rises. So here's another one, and this is what we need to use now, which is the assert. Oh, I've looked only at the first table, I suppose. Assert rises, and we can check whether the function raises a particular error. Okay, let's do that. Warns and logs. Okay, so assert rises. Then we want the exception function and arguments for the function. So the exception that we want to see that is risen would be this type of exception, type error. And this should be risen if we say polyline of, say, some numbers and then string, like that. Okay, let's try doing it ourselves. So if I say polyline equals polyline of some numbers and then a, which is a string, then could not convert string to float. And that's a value error. That's a value error in here. Okay, that's a value error. That's okay. Let's check that we get some error, but the assertion, we should put a value error here. And here we are. This test did not pass. Tests for the initializer, trace back, assert rises, name error, name assert rises is not defined. I guess that would be unit test assert error. How is this done? Self? Self. I didn't want that. So the test should be attached to self. Assert. It's also misspelled. Could not convert string to float. Run one test, failed. Errors 1. So it seems that the error that we're getting is the error that is that takes place when we're trying to do this. And let's see. Okay, let's look if we're doing things right. And we should read this assert rises description. Now it's a callable and then the arguments. So it seems that the arguments should be given separately to the assert rises. Assert rises value error polyline, and these are the arguments. How about now? Oh, now it's okay. So okay, so here's how we test whether the function raises an error. It's just that we need to give a function polyline, and that's of course calling polyline init with a particular set of arguments. Wonderful. So this test passes. We cannot pass string to the initializer. Now, can we pass something else rather than the NumPy arrays or matrices maybe, or different things for the arguments x and y? Let's see how to do that. Well, so what we want to do is we want to test whether polyline called with particular set of arguments, say 1, 2, 3, 4, returns or is initialized in the right way, so to say. How do we do that? Well, we can check the representation, right? So let's write the representation for this object, and then check whether the data that we've given it is understood correctly using the representation. But I guess before that, we should change the we should finish the initializer with the label, and so let's put this. Check different data passed as x and y. All right. So let's come back to that in a little bit, but let's put here the label. Label is going to be just label. You know, this thing is what passed, and this thing should be the attribute of the object itself, right? So to create an attribute, I'm just going to say self.label. That creates the attributes for the object that we are creating with this init statement. Should we check something? The label is going to be initialized to no label. If the label is passed, then it will have some text. Well, if strings are passed or something like that, let's convert it to string. I don't remember how to do that. Convert to string. Anything to string. Not integer, anything. I want to convert anything to string. Well, I guess that's simply just printing that object. So we can say, you know, here's the string that will hold the representation, and then we format label, give it the data label. Now this label is coming from the arguments of the function, and so this is going to be string label. Well, to be sure that it's a string, we should have here something with s. So s is the conversion to string. Okay. Now I forgot to add self to x and y over here, because we want x and y to also be the attributes of the object that we are creating. This is all that the object should hold according to specification, right? X, y, and the optional label. So label is optional, x and y is here. So let's continue testing, and here we are. If we just print PL, what do we get? Could not convert string to float. Test. Okay, yes. So here it's the same thing. That's the value error. Now, if I give it two vectors for x's and y's, and then the label, everything goes fine. But okay, if I give it a number, say for example, now the number unknown format s for the object type int. So it's another value error. So this could not be converted to string. That's the point. Okay, so we can write another test with assert rises. Say we started with some numbers here, but then give something which is not a string. Well, let's just give it a number as a label. Okay, and it should erase value error here. So test one. One test is done, and it passed. Wonderful. So both of this have passed, right? Yes. So both of this checks, both of these asserts are passed. Very good. What else should we check for to make sure that this initialization is correct? Well, we should probably, I mean, we are assuming that the axes are, what I'm thinking about is that axes are going to be the grid on the x-axis, and then f of x, the y's, will be the points where the function was calculated, and then the approximation, the linear approximation, will be something like that, right? They're connecting these lines. So a worth check is to check whether the length of the x and y is the same, and maybe even convert them into the one-dimensional arrays in case they are matrices or something like that. All these troubles with checking the past argument types and such is to make this code robust, right? So when we're working with Polyline, we don't want to worry whether passing a list or an NumPy array or an NumPy matrix even. It should basically eat everything that it can, but also raise errors if we pass something that it doesn't know how to deal with. And this ensures the robustness of the code that we'll be using this class. This is the reason that we're going in such a trouble on this initial step. So I think we should say if x size doesn't equal y size. Now I have to be careful again because x is now self x and y is self y. Size gives the number of elements. So first self x self y should be reshaped. Well, that's another line, and that doesn't look all that well. Let's reshape them here, both of them. And what do we reshape them to? Dimension should be given as a tuple, remember? It should be one one-dimensional array. Let me check it here. So if A is NP array, and we'll have a matrix here with 2 rows, 1, 2, and then say 5, 6. We don't need anything else. Print A. Yeah, here's the matrix. And now we want to reshape it. Yeah, we need to give it at least one dimension. Cannot reshape array of size 4 into shape 1 something. How about 1 minus 1, where minus 1 means that, figure out the shape yourself. But see, it's still a 2-dimensional array. So in order to get what I want, we need to squeeze as well. So get rid of the dimension which has only one, which is a singular dimension. This looks kind of ugly. So maybe there is a better way. And indeed, there's a command called Ravel, I think. NumPy Ravel. And as you can see, it says return a contiguous flattened array. That's exactly what we want. We want to just consume the data from any size, and it converts any size array to a 1D array, a one-dimensional array. Okay, so all we need to do here is to do Ravel. All right, and now we can just check the size. The size is going to be scalar, and if the size is not the same, then we should raise value error with a message, the to polyline should be the same lengths, like that. Okay, we can write a test right away for this. So we want raise value error if the polyline is initialized, now without the label, with arrays of different length, and the test has passed. Okay, so I think that's all we need to do for the initialization. With 3 arguments, vector of x, vector of y, and the optional label, all should be accepted. Let's now work on the representation. A representation, as we said, it should be, it can be anything in principle, any array or any object that represents this object, and we want a string representation. So we just want to create a string from this object that represents it, and then just return it, right? So what should we return? Well, we return polyline with maybe so many points, labeled something. Okay, we add format here with how many points? How do we get the length of this polyline? Well, maybe we can also implement the length. It should just return the length of self x. We know that x and y are of the same size, right? Or it can just return the size, self x size, the number of points. Let's check that really quick as well. So say A is going to be polyline with 1, 2, 5, 6, print length of A. And the length of A is 2. How about if I add some numbers here? Well, the input arguments to polyline should be of the same length. That works. See, we've passed. Oh, this is a syntax error. And now length of A is 4. Very good. Here we can say this is string representation of polyline. So format, we need length of self. Points labeled self label. And let's then list axis equal /n is new line, right? Y equal like so, and that's it. And here self x, self y. Let's see what this does. This is length of A, but if we say just print A, here's what we have. It's a polyline with 4 points labeled no label. Well, maybe labeled should be taken into some sort of quotes. Labeled no label. Why is there a double quote? Silly Julie. Jupyter editor. Polyline with 4 points labeled no label. And here we have x's and y's. But by the way, y axis and y's here are row vectors. That's interesting. because I thought we would have them as one-dimensional arrays. So is there anything wrong? Ah, yes, there is, right? So the string representation for x already has the brackets, and I've put new brackets in here. That we shouldn't do, because that's quite misleading. That makes you think that they're row vectors. But actually, without the brackets, they come out with brackets. We can actually check by saying, let's also print ax. Right. Well, of course, separator should be new line. Yeah. So ax is an numpy array. We can see that by also typing type of a.x numpy array, and finally the shape of ax. That's 4 by nothing. So it's a one-dimensional vector with with 4 elements. Okay, that's the representation, and now I'm back to checking whether our constructor can take different objects as x and y's. So here's the 1, 2, 3, 4, 5, 6. You know, if I make this into matrices, it will do the same. Now, if I make it into row, well, these are not matrices really. These are lists of lists. It will do the same if I have array. It will do exactly the same. So essentially, that means that the this conversion of the x and y is the one that we need to ensure that all types of data that can be converted to the format that we need can be worked with. Okay, so you know, I've just made 3 manual tests. Let's make sure that this test also can be done in automatic fashion. And I'm thinking of checking the output. Okay, I'm thinking of checking the output, and I think I should go back to the unit test manual and see, for example, assert multi-line equal. Test that the multi-line string first is equal to the string second. When not equal, a diff of the 2 strings highlighting the differences will be included in the error message. This method is used by default when comparing strings with assert equal. Okay, let's do assert equal then. Assert equal. There we go. So we can represent a polyline as a string like this. And we can check whether we can say here self assert equal like that, right? And here there will be string representation of a particular polyline, say this one. And we want to check against this string. Wonderful. And this now can be done many times with different input types to the constructor of the polyline. So here, for example, I can say, like I did manually. So it could be 1, 2, 5, 6, like a list, and then 5, 6, 5, 6 as list of lists, or list with 1 element, which is list itself. And this is now converted to string, and it should be that. Now, it could be without NP-array. It could be a list of lists, each of which is 1 element. And that should be the same. And finally, it could be something with NP array made out of this. And a list as a second argument also made there. And it should return the same string. So let's, yes, all of this pass. But see if I change something in this one string here, that's against which we're checking. Then we have a fail test, a test to the initializer, polyline with 4 points, no label, and there's a difference here, right? This L is not here anymore. And the same thing that, why do we need all of this unit tests? So right now everything is passing, and I'm developing this class, and it works as I'm intending it to work. But imagine that, down the road something changed, and instead of this line, we will have a line that doesn't convert the x and y's into one-dimensional arrays. And let's just try to pass these here. Immediately we see a problem. So something has changed, and some tests are not passing. Assertion error, polyline with 4 points labeled blah blah. Polyline. So see, there are differences in the outputs of these lines. In particular, this line is completely deleted, and this line is added. Or this is the difference in the representation. Can we see it over here? What's the difference? Well, it's gonna be certain difference. What happened is that this array keeps its dimension if we don't ravel it, if we don't make it a one-dimensional array. And this is not what I'm intending. And if by any chance there was a change in the main code that changed the important thing that I wanted to check up front, then I would see it right away. But right now everything works, so I can develop further. So unit testing, this is essentially what it is. It's just ensuring that the code that we develop is keeping its functions in the way that we intended it. Okay, so I think we're done with initializing and representing a polyline. Now we need to work on the call. Call, if you remember, that's going to be for any collection of points x in any shape, actually, we should be returning the values of this interpolated polyline. Returns the interpolation of the, well, let's say the values of the polyline computed for given points x. And for this, we need to use the interpolation routine from SciPy. And let's see how it works. Interpolate interp ID x, y, erase kind linear access, copy true, bounce fill value none, assume sorted false. And I think there are more instructions here. The output should be the same shape as the input. Use SciPy interpolate ID function and return none for extrapolated values. Set bounds error false, fill value none. Okay, so this is basically referring to, as it seems, bound errors false, fill value none. So it speaks of the arguments of the interpolate. What are the main arguments? Real values x, y. X and y are arrays of values used to approximate some functions. Oh, that's exactly what Polyline is doing. This class returns a function whose call method uses interpolation to find the value of new points. This is important. This class returns a function. Let's make sure that SciPy is included. Oh, and we've already imported interpolate. So I can say interpolate interp 1D, one-dimensional. So here, interp is going to be a function that is returned by this call. Okay, and this call needs to have the data x and y. Well, of course, that's self x and self y, the data that the polyline is holding. And then we need to add this additional arguments which are given to us. Bounds are false, fill value nan should it be in quotes? Fill value if array, if two elements. Oh, it should be just nan as a value. Is it written like this? I'm a little lost here. If not provided, default is nan. I guess we can just skip it. No? How do we access float now? Here we are without num. Oh, my monitor is doing something funny. Math nan, but we already have numpy. So let's see numpy nan. Miscellaneous. Special values np nan. That's all we need. So fill value is going to be np nan. Now this is going to be a function which should be applied to the data where we need to calculate the interpolation, and that's exactly the return. The interesting thing is that the interpolate function, I think it preserves the size, the shape of the data that it's given, the points where the interpolation should happen. Non-representing find behavior. Okay. So here's the example. A range x interpolate. So here's the interpolation. Now f is the interpolation function. X new is some other points, and y new is the interpolation at these points. And now we can plot them, and here you can see how the linear interpolation connects the blue dots, right? The blue dots are printed with this function. Yeah, x and y are in dots, x and new are in as a line. There we go. All right, so that's the call. I think that's all we need to do for it, but let's test it. Oh, I just ran that cell and I got an error. Return equals. Yeah, of course we don't need the equals. Just return the interpolated values. So now I can print a as a polyline, but I can call a axis as 1, 2, 5, 6, 5, 6, 5, 6. It's going to be a nan, right? Because 1, 2, 5, 6, these are my axes, and I've called it for interpolation outside of that. But if I call it at 2.3, for example, 2.3 is between this point and this point, and so I'll get an answer between 6 and 5, and 5.9 is something which is close to 6, and that's because 2.3 is closer to 2 than to 5. And then if I call it with, I'll say, list of data, then I get several interpolated values. Like this, and 23 is outside of the bounds, so we get null. Okay, this function seems to work. Definitely worth writing a new test. And we've tested init and wrapper, I guess. Let's try writing a new test here. Test call. I guess we can assert equal. Let's create a polyline just like that. And here's our call, and this should be equal to this list. Well, none is not going to be defined unless we say np now. I wonder if this will go. No. Failed, one error. The truth value of the array with more than one element is ambiguous. Okay, so it shouldn't be equal, but what should it be? All equal? Not equal? Is there something all equal? Not equal, greater than. So I'm going through the assert methods of the unit tests. Not equal, true, false raises almost equal. What is almost equal? Second I appropriate. Difference. Okay, almost equal is good for floating numbers. Multi-line equal, list equal. There we go. This is what we need because we are returning the list here, right? List equal. Still failed. First sequence is not a list. It's an array. Okay, we've returned an array. Well, let's just convert it to list. That's probably the easiest thing to do now. List differ. First different element is 1, 5, 3, 3, 3, and 5, 3 there. So it's these elements which differ. Well, that's of course because they are floats, and so we shouldn't compare them directly. This attribute controls the maximum length of diffs output by assert method that report diffs on failure. The default is 80 by 80. No, that's not right. Test that first and second are approximately or another by computing the difference rounding the given number of decimal places. Places 7 and default is 7 and comparing to 0. Assert greater than. Okay, so we should do this, but to compare floats. But now we will have problems because these are lists, right? Test polynomial has no attribute almost equal. Test. Oh, assert, sorry. Yes, it doesn't work for lists. Okay, well, let's see data. This is interpolated data. And we call it data not. And data 1 is going to be this data. And let's compare them element by element. Or rather, let's say that we want data not up to the which element? 0, 1, 2. I don't want to include none. So we want to compare the 3 up to third, so it's 0, 1, 2. And we can just sum them up. And let's compare the dt1 up to third and then sum them up. Well, I guess the sum is not going to work for lists. Okay, so we'll make an umpire array out of this one, or we can say as array. Okay, now we're fine. And let's also compare that Assert is none, something like that. None. There should be a check for an n. Well, let's just make it maybe assert true. Assert true. Assert true and check whether the last element, the third element, is simply none. Let me just check that numpy is none exists. Yes, it does. Okay, how about now? Okay, we ran all the tests, 2 tests, and they all check out. Okay, so we've created the call. And again, you know, a slightest change here. For example, let me call this. Let's say we didn't do this. And we run the tests, and it doesn't go through. And that's because value x is above the interpolation range. So now we have a problem with the interpolation. We've basically broken the interpolation. But what about this false? We'll put that back in, and they all pass. Now, why do they pass? Why does this line give the same passes the test together with this? That could be for 2 reasons, right? It could be that the test is not written adequately, which is the problem, or in our case, the thing is that the fill value is none by default, and that's what we read in the manual, and therefore we are sort of being on the cautious side here to ensure that if the interpolation routine in some future versions changes this default behavior, then we will still have none in there. But so far, even this simpler call passes our test. Now you can again see why the unit tests are important. If in the future version of the interpolation routine this default behavior changes and we rely on the default behavior, by relying I mean that it's important and we've written a test. If the default behavior changes, then we will catch that change using our unit tests. But to be on the safe side, I'll leave it like this. What else should we do? Call. Then we should have add. The concatenation of two polylines, and that will overload of plus to concatenate two polylines. Okay, here I'm gonna write the test first, and this is the way it should be done, actually. So test add. Let's see. Let's create 2 polylines. A 0, 0, 0, 0, 1, 1, 1, 2. For x's, and the same number. It can be just the same list here. And another one for b. Let's say 9, 9, 1, 2. 9, 8, 1, 2, like that. And now what I want to get is I want a plus b equal a new polyline which puts together the points of the first one and the second one. So how can we check that? Well, let's call this polyline a C polyline, and let's assert that self-assert. Let's go back to checking the lists. Assert equal list. Assert list equal. Let's check the list of a.x, b.x, but we need to convert these to lists before comparing. Just like that. Sorry, that was not right. Cx, and what are we expecting of C? Well, we're expecting the list in the A be put together with the list of the B, like that. And this is in place of X, and in place of Y, let's put some new numbers in here. We're expecting these numbers to be concatenated with 9, 8, 1, 2. They're all too similar. So let's say 3, 4, 8, 7, 9, 9, 3, 4, 9, 8, 7, 8, like that. And if we run it now, the test is not passing, right? One error, unsupported operand type S for plus. Unsupported operand type, well, that's, I guess, because we didn't run this. Now we do have add to implement the plus. Will it pass now? Attribute error. Non-type object has no attribute X. Okay, so we are not returning anything. And obviously, this addition doesn't work the way we want it to work. So the way we want it to work is now already in the test. And so all we need to do now is to write the code that passes this unit test. Okay, so how should we do it? How do we connect two NumPy arrays together? Because essentially what we need to do is we need to take self, check that it's a NumPy array. Well, self is always a NumPy array, otherwise this wouldn't be called. Check that other is the NumPy array. If not, is instance other, not the NumPy array, of course, but polyline. Polyline raise type error with the description that only polyline can be added to another polyline. And this can be checked too, right? So after we can put it here and assert raises. Over here, for example, it should be type error from this should be a function with arguments, right? So the function should be add. The arguments should be a and say a string, and maybe a and a number. It still fails, which is good. Name add is not defined. Is it plus? Plus is not defined. Okay, let's look at another way of assert raise that we can do here. I remember noticing that we can do a multi-line thing like this. Self assert raise raises type error. And here we can try to do something which would raise an error, like a plus string or a plus number. Okay, that would be sufficient. Well, it still fails, but it fails type error not raised. Oh. Should be raised now. Non-type object has no attribute X. Okay, so we've done this. Type error is raised, and now we are failing over here. Okay, wonderful. And that's because, the return, which is C, and C is now becoming none because we're not returning anything from add. Okay, now we know that self and other are polylines. And now we want to concatenate x's and y's and say label and then say return polyline x, y, and label equals label. So we want to take the x's of two polylines, put them together in one list, take the y's of the polyline, put them together in one list, and then create a label. And maybe the label should be something like, maybe it should be something like self label plus other label. So that's basically a concatenation of labels with a plus in between of them. Okay. Now, how do we put together the NumPy vectors? Well, quite literally, we just say NumPy concatenate. I did a little fast search here to make sure that A1 and A2 are of the same shape except dimension corresponding to axes. X is a 0 by default. Concatenate self x other x. So we're putting together the x's and we're putting together the y's. And let's try. It failed. Only integer scalar arrays can be converted to scalar index. Where is this coming from? I should read this once again. Okay. We need to give it a collection as a tuple. Yes, a lot of the times this is how it should be done. So all the NumPy arrays to be concatenated should be in one tuple. Oh, and now we're passing the test. So we've written the code that does exactly what we wanted when we were writing the test, and therefore we can be sure that the code is performing to our expectation. And that's why writing the unit tests is so important before actually writing the code. Okay, we've done add. And now we want to do a little plot. Should make a plot of the polyline. Okay. And now this will be just a simple function here for self. Makes a plot of polyline. Let it return the axis just in case. And let's start with creating the axis. PLT axis. And then x plot self x, self y. And let's make a plot also care about any additional arguments that might be passed. They can be passed to plot so that, from the outside we can change color or thickness of lines and things like that. Set labels. How do we set label? Well, we'll return the x, and therefore it would be possible to do things like, A is a polyline, so A plot. Polyline object has no attribute plot. No, it does. Here we are. This is the polyline. But now if we say x is equal a plot, now we can add to that x, whatever we want. X lim of 0.10, for example. And it doesn't work. It doesn't have x lim. Oh, I guess PLT then should do it. Yes. The axis we still want. We still may want to access afterwards. But here we can say, color equals red, and the polyline will have red color because this argument that we've passed to the plot function is captured by all these keywords, and they are just transmitted to the plot from the PLT, from the matplotlib. Or better yet, we can say label equals test, and then we can say PLT legend. And it will write the name of the line here. Now, what if we want to plot multiple polylines on the same plot? Say B is another polyline, and it will be 1, 4, and here 5, 7. And we want to plot it in blue and say test 1. What's wrong here? What's wrong is this NP array has a bracket that is not converted. Aging an access using the same arguments as previous access currently reused the early instance. In future version, new instance will always be created and returned. While warning is suppressed and the future behavior ensures. Okay, we're not doing something well. Direction warning. Deprecation warning. Access using the same argument as previous access currently reuses the earlier instance. Okay, so the fact that we've gotten this plots at the same on the same axis is actually by chance, and that's because when we created new axis, it used the one that already existed. So let's add the x argument to the plot function so that the x can be given if we want it, and then we can say if x, if x is not given, then let's create the x. Otherwise, don't create an x. And now we can say x equals x, and PLT show to finalize the graph. Okay, now we can give it an x and put this this new plot into an existing axis. This is also useful if we want to create subplots and create axes outside of the main code. Okay, I think this is good for the plot. Let's not check the plot functionality in the unit test. And finally, we get to the intersect. This should be a method as well. It will take two polylines, myself and other, and returns the NumPy array of intersection points. Now, each point will have two coordinates, x and y. Should it return the NumPy array or something else? What's the best way to do it? Well, let's do a NumPy array of intersection points, two-dimensional NumPy array of in rows. So it's like we will have, returned a matrix like this with x and y's, and each row will be a separate point of intersection. All right. How should we do that? So let's first check that the other is also a polyline, just to be sure. And it would be nice to write the test for the intersect as well before we actually do anything. But it's a little bit hard to come up with the example that we can that we can pre-calculate. So first thing that we can do is, okay, let's take, well, maybe these, well, let's take these two. Let's see, maybe we need to change them. But we can already assert the type error, right? So it's going to be a intersect something else, and if we pass not a polyline but something like a string or a number, it should raise the type error. And sure enough, there's an error, 3 dots, the 3 tests are running fine. 1, 2, 3, and the fourth we get an error. Polyline object has no attribute intersect. Does it not? We probably didn't run that. Now it passes. It passes, and that's because we already erased this error here. Okay, but we need to do something more. And as I said, we have an exercise where we've calculated the intersection point of 2 line segments. So let me go into that exercise, 9, I believe, and grab the code from here. Yes. Where's the code? Well, it doesn't have it here, so I'll have to grab it from some other space. Okay, so here's some code that we will pretend comes from the solution of the exercise 9. And this is a function. Let's see what it does. So it's supposed to have some heading here. And let's call it intersect segments. I want this function to be only accessible from inside of the this class, right? And the way to do it is to put double underscore in front of it. This is the Python convention to mark the private functions. So I want intersect to be callable from the outside, but the double underscore intersect segments I only want to be callable from the inside. Okay, so let's see what happens first here. We have to give this intersect segments function 8 numbers, right, which are the coordinates of the ends of 2 different line segments. So 4 points altogether, 2 for each line segment, and each point is given by 2 coordinates. So 8 coordinates. And here's how it's done. We can say args in the function, and now if we call it with 8 numbers, they will be unpacked in the following way. This is really unsafe way to pass numbers, but since this is going to be just the internal function, we don't need to make the interface for talking to this function all that pretty. So here's how it's done. x1, first line segments x1, y1, x2, y2. Second line segments x2, y2, x1, y1, x2, y2 for the second line segments. All right. Then the function does this interesting check, which is called the bounding box check, whether the intersection is possible in principle. And the idea here is that if you have, in some coordinate plane, a line here and a line here, to check whether they could possibly intersect, you can look at the boxes that they define, these rectangles, and see whether these rectangles overlap in some way, right? So the overlapping rectangle would be something like this, where the coordinates of this corner and this corner satisfy particular inequalities. Now, if the rectangular box overlap, it doesn't mean that the lines intersect, like so, for example. But when the rectangular box do not, or these bounding boxes do not overlap, then we know for sure that the lines do not intersect. And this is what's done here. This check is fairly simple. We just have to write it carefully, looking at all different possibilities. If the bounding boxes don't overlap, so this check doesn't pass, then the function returns none immediately without doing any computation. And none is returned to indicate that there is no, this segments do not intersect. Now, if the bounding box do overlap, then we go back to this method here, and we form the system of linear equations. Matrix A, according to the specification here, well, this is all in the solution of the exercise 9, but I'm going through it just to repeat. So here's the matrix A, which is formed from these 4 rows, written explicitly and exactly as over here. And we have a vector B, which is a column vector. Well, here it's a one-dimensional vector. It doesn't matter for the NP-linear solve. But it should be written as a column vector from top to bottom. So minus x11 is the first, minus y21 is the last element here. And the solution is unpacked into T1, T2, and the intersection point. Okay, finally, the check that we need to do is to see whether T1 is within the unit interval and T2 is within the unit interval. And if both is true, then we return a tuple which contains the coordinates of the intersection point. So this is how this function works. Okay, how is this function can be used? Well, here we are. We have to find the intersection of the 2 polylines, but we can only check whether the line segments intersect. So the simplest algorithm I can think of is to just compare each pair of the line segments from the 2 polylines. Okay, let's implement that. That's not the best. It's not. It might not be the most efficient. Although, can there be anything better? Probably not. And let's collect the data on the intersection point into the x and y arrays here. They're just local arrays. And I want to initialize them as empty lists. So we will use append. We will use append to put data into them. Maybe that's not the best way to do it. Let's initialize them as the so, and we said that the output should be an array. Let's initialize the out as the empty array of the size say 100 by 2. Right, where the 100 is the upper bound on the number of intersections. Now, how many intersections can there be? If 2 lines and we know their length, it could be that each segment intersects with every other segment of the previous line. Can a particular segment intersect every other segment? So the situation I'm thinking about is something like this. One line is like so, and another line is like this. So 1, 2, 3, 4, 5, 6, 7, and this is just 1, and 1, 2, 3, 4, 5, 6, 7, right? And if this line looks like this, then we will have the 14 intersections, right? And this is the upper bound for sure. Okay, so the upper bound here will be self length, or just say length of self, times the length of other. This is the upper bound. Of course, many polylines will not have as many intersection points, and so we will track the number of intersections points as with the integer. Let's make some comments. Space for the intersection points and this is number of intersection points so far. Okay, this is good. So this is the output, and we want, the way we will use it is going to be like this. We will say k everything. Is this good enough? No, k 0, comma k1 is self double underscore in production. So but if this returns none, that's not good. That's not good. So how do we do that then? Yeah, we have to calculate this point separately. Point equals whatever returns from there, and if pp, so it's not none, then we put this into here like so. It will return a tuple, right? So pp could be a tuple, and then we use it as a tuple. We can just do it this way. So then we unpack the tuple. Otherwise, it is none, and then if will not fire. And here we can increment k by 1. So what's going on is that we should go through some loops, and for each possible combination of the segments of the two polylines, we should compare or try to find the intersection point of these two particular segments. And if it is found, then the coordinates are in pp, and pp can be unpacked into the correct space, and k can be incremented to say that the next, and to get ready for the next space. And of course, k starts with 0, so we'll first fill out the 0th row of the out, and then in the end we will return out. Okay, that's all we need to do. And now we need to organize the loop over the polyline. I just had an interesting thought. So if the length of polyline is given by the size of x, how many segments are there? Well, there's one less, right? So a polyline takes 1, 2, 3, 4 points, but only 3 segments, like a fence in the posts. Okay, so we need to take that into account, and that actually means that this length here is the upper bound can be calculated slightly less. Oh, I lost it. It is length minus 1 times length of other minus 1. Because length is counting the points. And so the upper bound is here. Okay. So now we have to loop over the segments of the polyline. How do we do that? Well, what is a segment? A segment is essentially 4 coordinates for the points, right? So we have to slide over the lists of x and y and collect the points in the correct way. So let's just say P1 in okay, I see. I think this is a good way to do it. So we can zip self x with self y, and this is going to create the pairs, right, of the points. but we only want this x and y's to be in the going until the next to the last. Okay, let me check the Python zip function. Can it zip more than just two? Two lists. Built-in function. Zip. Iterables. So I guess iterables can be multiple iterables. Eth tuple contains the eth element for each of the argument sequence. The iterate stops when the shortest iterable is exhausted. Wonderful. So we can actually zip x, y, and then self x, but starting from the next second point, right? So starting from 1, and self y also starting from 1. Okay, what do we get through this combination? We get x1, y1, x2, y2 of the first polyline, and that's pretty much exactly what we need here. x11 is the first line segment, 1, 2. So the first index here is going to be 1 everywhere. x11, y1, x12, y12. Okay, and this will create the quadruples of numbers, where the first is going to come from the first element of x, and this x12 will come from the second element of x. The zip will exhaust as soon as the shortest string ends, which is this one. So the last point will have the next to last element of x and the last element in here. So every time this will look like so. So we have x's, like a line with different dots, and y with little dots. And this iterable is, or this zip, will return this point, but also this point and this point. And then this whole thing, you know, will move towards the end of the list. And that's what zip does. Okay, and we can do exactly the same for the second polyline in the nested loop here. And this will have the second set of indices like so. And instead of self, we need other in here to access the points of the other polyline. All right, so now we have all of these points, and remember they have to be given in the right order to the intersect segment. In which order? Well, I can just copy them from here. This is the first 4, and this is the second 4. And I trust this is exactly what we need. That's exactly what we need to do. And now this just needs the correct alignment. Like so. So this is a double loop that goes through all segments of the two polylines. And for each combination of the two segments, we're searching for the intersection point. If we find it, we put it into the output bracket. Okay, final thing to do is to say that we don't really need this output to be as large. We can say that the out is simply out of up to k with all of the rows. Right? Because if we didn't find any, then this out is going to be just 0. Or it's going to be an empty set. If we found one polyline, one intersection point, then k is going to be equal 1 because of the increment. And then we will output everything up to the first. I think this should work. Let's try to do a visual graphical test. Okay, something is not working here. Polyline, random, random, first line, second line, intersect. Okay, that should be fine. Whereas the arg is not defined. In where? In here. Arg is not defined. It's inside here, and it should be args. Just like that. Let's see. Too many values to unpack. Expect 4. So what are these args? Expect 4. Let's check how many args we get here. One, two, three. No, wait a second. Where are the args? Ad hoc debugging. Oh, we getting a polyline. Interesting. Why are we getting a polyline in this args, in the intersect segments? We should probably check what's going on here. Self-intersect we haven't done yet. P1 intersects P2. These are coordinates. We're fine. Self-intersect segments and all of these coordinates. So x11. Let's print all of these numbers. As a tuple, that's okay. So all of these numbers are 1, 2, 3, 4, 5, 6, 7, 8. So all the numbers are actually passed in the right way. But polyline with 10 points labeled first line. Somehow the first element here that the args gets is the polyline. Well, of course, I forgot self. That's what it is, because this is going to be called as a self method, even though it's a private method. The first argument is always just itself, just the object itself. Okay, now I don't want any of those prints anymore. It seems to be working. Okay, let's go here. And this seems to be working. Well, let's try to plot what we've seen. Oh, look at that. So we see that they multiply the same warning as we had before, right? So what needs to be done here is that x needs to be saved and then explicitly given here. No handles with labels found to put in legend. Yeah, okay. That's because here we should say. Actually, you know, there's a label in the polyline. Why don't we use the label in the plot? So here, plot axis, self axis, label equals self label. That would be logical. Oof. Labels. I misspelled something. Label. Here's our graphical test, and I can see that the intersection points, which are just plotted here after they're being computed by this intersect, are plotted exactly right. And we can run this many times, and you can see that all of these intersection points are actually plotted at the intersection points of the polylines. Brilliant. That's working exactly as we wanted. This is the beauty of the graphical checks and the graphical debugging. I don't know if this can be automated as a unit test. This is really not a unit test. It checks a whole complex behavior. But you can see that, by just looking at this picture, you can see that the intersection points are plotted right at the intersections. And you should also check whether there are any intersections which are not tracked. And I don't see any here. Okay, the last function to implement is the self-intersect, the last method. Self-intersect is basically just searching for the intersection points of the polyline itself. Okay, and therefore we are going to be doing exactly same work, but now the loop is going to be slightly different. Two of intersection points in rows between two polylines in rows. Self-intersection points in rows. So here we don't need to check for the other type. The upper bound is going to be a little bit different, but everything else is pretty much the same, so I'm just copying it here. The upper bound is going to be just the square of the of my own number of... Oh, it's not very accurate upper bound, right? So what's the worst case? You need 3 segments to get 1 intersection point, and then each segment after that, can it intersect all of the other? It's hard to say. Well, the square is going to be definitely an upper bound, although maybe not very accurate. So this is the empty space. Number of intersection points so far. So really what we need to check is that we are looping through just self independently, right? So first these two loop definitions are exactly the same. The only problem that I can see is that if we're giving exactly the same intersection line segments to the to this intersect segments routine, what is it going to do? It should output none right away. The bounding boxes is going to be exactly overlaying, so there must be another check here. How do we check that? I'm thinking to compare the values here. So let's try to do this. This arguments minus the second half of arguments, they're aligned nicely so that we can compare them. And if that's less than some small number, then I return none right away. So this is basically the check to identical segments. Check if segments are identical, then they don't intersect. Let's see here. Can we try to do an A? Let's delete all of this. Print A. Self-intersect. This is just a method that we printed. How about if we call it unsupported operand type for tuple and tuple, the minus. So we cannot take the difference between the tuples. Okay, we'll have to convert them to lists then. Oh, NPy arrays. And of course we should check for all being this close to each other. Okay, so self-intersect is 0 and there are no errors. Wonderful. Let's go back to this graphical test. And here we can see, well, self-intersect is now spelled with an underscore. Here we are. It seems to be doing the right thing, except sometimes, what is this? How can it be? It goes there and then back? I'm a little bit confused. So sometimes it puts a dot between the intersection of two adjacent lines. The dot that shouldn't be there, like these ones and this ones. So that's comparing this this segment here with this segment and finds the intersection point where they just join. Okay, so that's probably another test that we need to include here. A test for identical start and identical start and end of the segments. Share a point. Okay, if the segments share the point, then they don't intersect. Okay, how do we do that? Well, this is one point. We can compare it to this point and to this point. This is first 2, and fourth to 0, 1, 2, 3, 4, 5. So 4 to 6. And then 0, 2, so 2, 3 up to 4. No, let's go systematically here. So first these two, I want to compare to these two and these two. And this is 6 and up. And then 2 to 4, I want to compare to 4 to 6, and then 6 and up. And each of these cases, the segments share the point, and therefore they can not, they do not intersect. So what cases do we have here? Case like this, case like this, case like this, and case like this. Yes, there are 4 cases. Let's see. Let's try this graphical test once again. And there we are. So if the point is shared between the two line segments, it's not called the self-intersection. And self-intersection points are nicely tracked. Okay, now I don't need this cell anymore. And here's my class. Here are my tests, which are all pass. Here's my graphical test, which passes. And this is a random test that we can, high-level test that we can run over and over again to get different cases, maybe more complicated cases. And this is the beauty of visualization of the code in this respect. You can see that the intersection points are all found really well, and the self-intersection points are also found without any problems. Okay, so this is a complete class up to this specification. And even though we already had some modules coded up, as you can see, this is a really long video already. It's almost 2 hours. But I hope that you find it useful since I've talked about unit testing and sort of code development at large. This should be quite useful before the midterm paper. We didn't do the equilibrium model yet. So how should we do it? Well, that's fairly simple. Let's complete the equilibrium model. Let's call it demand, a polyline of some x grid or price grid, and the function demand of these prices. Okay, supply is the polyline of price grid, and supply of the price grid labels should be demand, supply, and the price grid can be some grid. Let's compare it to this plot here. It's between 0 and 100. And let's take 10 points to start with. And then we just have to essentially plot these lines here. P1 plot. Okay, let's call this one P1, and this one can be called P2 to save on some typing. Can't assign to a function call. What's going on here? PR, demand of PR. Why is this a function call? I think I have an extra bracket in here. So, yep, there we go. So what do we have? We have P1, P2. Oh, and then intersection has to be calculated as well, of course, between the P1 and P2. And now we have one intersection point right in the middle there. And this plot should be similar to the plot right above here, but they are not. The demand and supply. What's the difference? Well, the difference is, of course, the accuracy. So if we increase the number of points in the polyline, then there we go. That's now looking very much like what we had in the previous picture, and we can print the equilibrium. And quantity is this format. Intersections, there's going to be only one. So I guess that should be enough. Tuple index out of range. How about like so? Oh, still out of range. Okay. By the way, you can feel how it takes some time, right? There's one intersection point. It's at 27 and 7.07 here. So this is our equilibrium essentially. Of course, it's returned as a NumPy array with rows. So I should say here 0, 0, and 0, 1, like so. Oh, I'm sorry. Okay, that should do it. The equilibrium price is 27 and the quantity is 7. Here's our market equilibrium from the problem that we started. It takes some time because we are asking for pretty long polylines. But if we decrease the accuracy, It's going to be a little bit more jagged, but it calculates it in a much faster way. 10 is definitely not enough, although there's some approximation to the equilibrium. But it seems that 50 is quite enough to represent the shapes of the supply and demand curve fairly well. Okay, I stop here. I hope you find this video useful. There's another resource which talks about precomputation and visual effects, which I find pretty cool. All right, good luck on the midterm project, and I hope this coding marathon had been useful.